This week, we shall focus on DC-DC converters. We shall begin with non-isolated converters. You may already have heard about the buck converter, the boost converter, buck boost converters. That's the primary objective in this particular week's lectures. We will see how they operate, how they work, simulate, and then how to design them too. You have a DC voltage and you need to supply to a load which demands DC. However, you will see many situations where the DC voltage which you have, battery or coming from the rectifier filter, is of a value which is not directly usable by the load. The load may demand 5 volts. It may demand plus minus 15 volts for analog circuits. It may demand 3.3 volts or 1.8 volts for most of the digital circuits. So you need to see that a power interface, a power supply, something like a power supply is built, which will do this job of properly converting a DC of one level to DC of another level. So how is this done? One is by linear regulators. We use linear regulators were the most popular until the advent of the switched mode power converters some 15 years, 1.5 to 2 decades ago. The linear regulators are very accurate, very precise, very good regulation. However, they are not efficient. The switched mode regulators are definitely more efficient. There are no lossy components in an ideal sense, no lossy components within the switched mode DC-DC converters. However, the quality of the DC output that you get out of the switched mode DC-DC converters are not as good as a linear regulator. However, the DC-DC converters, switched mode, have become very popular, and they have improved in quality and performance over the years, and today they are most popular and they are used in most of the power supplies and DC-DC converters. Even in our PCs, in the monitors and any electronic equipment, the front end portion would be a DC-DC converter. So we shall try to see what insight that we can gain by studying these non-isolated and isolated converters and go towards understanding the real power converters, the DC-DC power converters, which go into most of the products today.
Let us discuss about the basics of the DC-DC converter. It consists of an input source, it could be a battery or the output of the rectifier filter, which we discussed in the last week. Then it contains a load which expects a DC voltage. Now these two need to be interfaced. The simplest and the easiest way of interfacing would be to put a resistor in between. This would be the simplest DC-DC converter. Now let us make the connection, wiring connection, so that we have a circuit diagram. Now that we have made the connection, we have the source, the intervening resistor and the load resistor. Let us give some names. We will call this one as Vin, the input voltage. We will call this as the output voltage. We will call this as the load resistor, and we will call this as the series resistance, which is in between. Now this is what will act as the drop, such that the output voltage is according to our wishes. Now let us say, for example, we have 48 volts at the input and we need 5 volts at the output here. The remaining 43 volts has to drop across this resistor. This would be the series drop resistor, and this is the typical concept that is used in almost all linear regulators. Now this resistor can be a varying resistor so that you can achieve regulation. So as the input voltage vary this resistor such that the output is at a regulated level, whether 5 volts or 12 volts or whatever voltage that you have set. Unfortunately, the problem with this type of simple DC-DC converter is that RS is resistive. There is a current flowing through this circuit. If there is a current I flowing through the circuit, then there is a dissipation across RS, and that is I square RS. Now this is a finite resistance, and therefore the power dissipation is finite, and it is this can be quite a huge power dissipation. Therefore, these type of regulators are highly dissipative and very inefficient. Now, our interest is to see that the drop in the series element is zero. How do you make that happen? We can make I square RS equal to 0 in two ways. One is by making RS equal to 0. RS can be made equal to 0. In another way, you can make I equal to 0. Now I is equal to 0 implies RS tending to an infinite value. So what does this mean? It means that when the switch is a short circuit, in that case the voltage across the switch is 0, there is no power dissipation. When I is equal to 0, the switch is an open circuit. So when you make the switch open circuit, the current through that is 0, and then also the power dissipation across the switch is 0. So the only two conditions when the switch is not dissipating power is when RS is 0 and when RS is infinity, when the switch is short circuit fully on and when the switch is open. So these are the two conditions that are permissible from the point of view of power dissipation in the series circuit, power dissipation in the series element. To achieve this, let us replace the resistor by a single pole, single throw switch as shown here. So when the switch is on, Vin comes to the output. When the switch is off, V0 is 0, and this way there is no dissipation in the switch either when it is on during conduction or when it is off during the open circuit situation. However, the voltage now V0 is no longer continuous pure DC. It is pulsating. When the switch S is on, then you have a DC voltage of Vin appearing here. When the switch is open, the voltage across V0 is 0. So it goes high, low, pulsating voltage, and this becomes a chopper. So it's called a chopped voltage, and this circuit becomes a chopper. This is not what we want. We would like to have the output voltage V0 as a pure DC. So which means that we would like to have a kind of a filtered circuit here. Now this could be a filter. And this could be composed of L's and C's. It could probably have an inductor, something like that, and a capacitance, something like that. These L and C's together would form a second order filter, and this chopper, switch plus the filter together will provide a DC voltage at V0, and together they form a switched mode DC-DC converter. There are many configurations in which this switch and the filter can be put together. If we have one switch, one inductance, one capacitance to make up the DC-DC converter elements, then we call it as a primary topology. In the primary topology itself, there are three possibilities. One is a step down converter or a buck converter. Another is a step up converter or a boost converter. Yet another, you have a step up down or buck boost converter. So basically a step down, as the name indicates, converts the input voltage into a lower output voltage. Step up converter converts the input voltage DC value into a higher output DC value or boosting it. Step up down converter can do either. Under certain duty cycles it will be step down, under certain other duty cycles it will be step up. We will of course look at all three types of converters in this week. All these three types of converters do not have any galvanic isolation, that is, they do not use any transformer. They are non-isolated converters and are pretty important, and there are many applications with which these converters can be used. We will look at its operation, we will look at how to go about simulating it and also to design it.
This is a chopper circuit. The switch is a single pole, single throw switch. When the switch is on, the pole is connected to the throw. The throw is connected to the positive of the input, which is V in. The pole voltage is same as V in, which is transferred to the output V0. When the switch is off, the pole is floating and the pole voltage is undefined. So also is V0, which is undefined. This is not a recommended way of drawing the switch. We have to replace this switch with a single pole double throw switch, where there are two throws and both the throws are connected to well-defined potentials. In such a case, the pole, whether it is connected to one throw or the other, will have a defined potential and therefore the output V0. The switch S is now replaced with a single pole double throw switch. It has two throws. Throw 1 T1 is connected to the positive of the input supply. Throw 2 is connected to ground. When the pole is connected to T1, the pole voltage is same as V in, which is transferred to V0. When P is connected to T2, T2 is connected to ground, and therefore the potential of V0 is 0, and therefore V0 has well-defined potentials at both positions of the switch. Yes. The chopper is now slightly modified. The pole is connected to the inductor L and a capacitor is connected across like this, and this LC forms a filter, a second order filter, which filters out the chopped waveform and gives a smooth DC to the output. The operation is pretty straightforward. When the pole is connected to throw T1, pole voltage is V in. The inductor starts charging up magnetically. The capacitor also charges up. When the switch switches to the other position, T2, this is at pole is at zero potential. The inductor current freewheels through the capacitor and the output load and discharges the magnetic energy into the capacitor and the load. And then again the cycle begins by the pole getting connected to V in. This is a DC-DC converter called the buck converter. Here the output voltage V0 will have a value less than that of V in. Let us define some nomenclature here. When the pole P is connected to T1, we will call it as S on, switch is on. When the pole P is connected to throw T2, then we say the switch is off. We shall now try to plot the voltage across VL. VL is one critical component that you will have to study, and the other component that you need to study here is the capacitance C. The voltage VL across the inductor. So let us draw a couple of axes. Let us have our x-axis, which is the time. Let us have the y-axis, which is the VL axis, the voltage axis. We shall put in some timelines, and let us say this is the on time of the switch when pole is connected to T1. This is the off time of the switch, again on time of the switch, again off time of the switch. So let us define it and name it in this fashion. S is on during this period, S is off during this period, again S is on, and then S is off. So let us plot the voltage that we see across VL. Now the VL will be a bidirectional voltage, so it may be good to shift this up so that we can see the bidirectional voltage on the screen here. When the switch is on, the pole is connected to T1, and the voltage at the pole here is V in. The voltage on this side of the inductor is V naught, and therefore at that instant the voltage across the inductor is V in minus V naught. So that will be the voltage that you would see at this point. And when the voltage when the switch turns off, the pole P is connected to the throw T2 and the pole voltage is 0, and the voltage across the inductor is now 0 minus V naught, which means that the voltage goes negative. And again, when the switch turns on, the cycle repeats in this fashion, the inductor voltage going positive and negative like this. What is very important here to note is that under steady state conditions, the area under the inductor voltage curve on the positive side and area under the curve on the negative side should exactly match. Let us give it some color. So you see the blue part on the positive side and the blue part on the negative side should match, which means the average voltage across the inductor should always be 0 in the steady state conditions. This will prevent the inductor to go into saturation. There will not be a magnetic flux build up and make the inductor to saturate. So it is very, very important that there is volt second balance in an inductor, and in the case of the capacitance, the average current should be 0. If there is an average current, there will be charge build up in the capacitance. So in the case of the capacitance, amp second balance should be there. In the case of the inductance, volt second balance should be there. These two are very, very important concepts which I will explain shortly.
Two very important components that we will use in most DC-DC converters are the inductor and the capacitor. Inductor is one of the dynamic elements that is part of the filter in most DC-DC converter. And the voltage across the inductor, as I was mentioning earlier, is a point that you need to observe, and that is a critical voltage. Likewise, in the case of the capacitor, which is also a very important dynamic component that we will be using in DC-DC converters, you have to monitor the current through the capacitance. Now let us look at the inductor first. The inductance L and the voltage across the inductance VL and the current I, which is flowing through the inductor, are related by the Faraday's law. So by the Faraday's law, if you look at that, you will see that VL is equal to L di by dt, and the inductor is generally wound on a core, on a magnetic core, which has N turns, and there is a flux phi which is flowing through the magnetics and linking with the coil. Now the relationship is as given here. VL, the voltage across the inductance, is L di by dt plus N d phi by dt. Let us look at this part of the equation, N d phi by dt. What is the flux within the core? Now the flux within the core is basically a rearrangement of this equation. Now let us say VL is constant across the inductor. Then integral of VL dt would be N phi, the MMF, or phi, the flux in the core, is 1 by N integral of VL dt. The important part here, VL dt, if VL was 0, then phi would be a finite value by this equation. If VL was not 0 but has an average value, which means it is like a DC value, then it starts getting integrated with time and keeps on increasing. And the flux also keeps on increasing when at one particular point, depending upon the material, it will saturate. Once it saturates, there is no longer an inductance effect, it will just be a piece of wire. Therefore, it is very, very important that VL doesn't have an average value, which means this volt second has to be balanced, as I had been discussing earlier. So in the inductor, very, very important that you need to know is that there should be volt second balance in the steady state. So this volt second balance is only in the steady state. In the transient, there will not be volt second balance because the energy within the inductor has to change. So in order to make it change, there has to be an imbalance in the volt second. But in the steady state, the volt second balance has to happen so that there is no build up of MMF. Likewise, in the capacitance, the governing equation is IC, which is equal to C dV by dt, where dV is the voltage across the capacitance, IC is the current through the capacitance. And rearranging this, you will get the voltage across the capacitance, which is 1 by C integral of IC dt. Imagine there is an average current, so which means there will be some equivalent DC value. The integral of the DC value dt means that this value will keep on increasing and the voltage will keep on increasing, which means that the voltage across the capacitor will go towards infinity and finally end up blowing the capacitance. And therefore, it is important that IC should not have an average value. IC dt should be balanced, that is, the amp second balance should be there. So in the capacitor, in the case of the capacitance, which is the dual of the inductor, there should be amp second balance during steady state. Very important to know, during steady state. And during the transient there will be some imbalance, so that the voltage across it will be built up or discharged. And once the steady state is reached, there has to be amp second balance cycle by cycle. Now this is a very key concept. In fact, the input output relationship of all the DC-DC converters, switched mode DC-DC converters, is based on these two important key concepts. The volt second balance under steady state condition is used to determine the input output voltage relationship of converters. The amp second balance is used to determine the input output current relationship. Of course, one could also use the volt second balance, determine the input output relationship, and assuming an ideal converter, determine the input output current relationship too. So remember these two. In fact, we will be using the volt second balance in almost all converters to find the input output relationship. If we revisit the buck converter circuit that we drew earlier, let us put some values here, generic values. Now this amplitude is Vin minus V naught, as we discussed earlier. During the time when the pole is connected to T1, the voltage across the inductance is Vin minus V naught. During the time when the pole is connected to T2, it will be 0 minus V naught, so it will be minus V naught here, the amplitude. Now the time, this is a time period which we will call T on, and this is a time period we will call T off. That is, for a duration of time T on, the inductor voltage is seeing Vin minus V naught. For a duration of time T off, the voltage across the inductor is minus V naught. Now let us apply the volt second balance to these parameters. Now consider this part, the equation Vin minus V naught into T on. This is basically the area of this rectangle, Vin minus V naught into T on. So this height into this width is the area of this rectangle, or this is the volt second of this part of the positive part of the inductance waveform. Now this is minus V naught into T off, which is the width. So let us add to that plus minus V naught into T off, this part of the area. So this volt second plus this volt second should be equal to 0. Now then we say that there is volt second balance. So this equation, if you rearrange, you will see that it is of this form: V in T on minus V naught, we can take it to the other side, minus V naught T off to other side, you have V naught T on plus T off. T on plus T off is nothing but the total switching period. So the total switching period is T on plus T off. This is Ts. So still further rearranging, we see that V naught is equal to V in T on divided by Ts. This is Ts. So this would be the input output relationship for this buck converter. This is just as an example. I thought I will mention this to you, the importance of the volt second balance of the inductor. Whatever may be the converter, if you take the volt second balance relationship of the inductor, you will get the input output relationship. This is the key concept that I want to convey in this particular video lecture.